So, chapter 7, we're talking about estimates. This is where we're going to really start getting into the predictive part of statistics. Before we get into it, one thing we need to talk about is the idea of the critical value. If you remember, if I have z of 0.025, z of 0.025, what that's saying is I want to know what is the z-score, what is that z-score that has an area of 0.025 to the right of it. Remember, it's always to the right. If you look up on your green packet, remember our green packet gives us areas to the left. So the area to the left would be 0.975. Ooh, I just found out it's easier to write with my hand than with a pen. Okay, so we'd be looking for 0.975, and that goes with the z-score of 1.96. We'll be using those critical values throughout this chapter, the next chapter, several chapters actually. So like I said, we're predicting things now. We're using inferential statistics. We use our data to try to make some sort of prediction about the population. Remember, that's really the meat and potatoes of what statisticians want to do. They want to go from, hey, here's the hard data, to I can make a prediction about the population as a whole. So we're going to start off with the population proportion. Now, we haven't necessarily talked about proportions as much as means or standard deviations, but a proportion is just basically a percentage or a fraction or a decimal that believes in something. So if I said 30%, oops, that didn't work. Oh, I need to get my pen out. There we go. If I said 30% of Americans believe in the death penalty, I'm just making that number up. 30% is my proportion. I could say it is 3 out of 10. I could say it is 0.3. All these are the same thing. So a lot of the data that you hear about is in terms of proportions, actually. It sounds fancy, call it a proportion, but it's just saying this many out of the total think this, or believe in this, or whatever. So it is what's called a point estimate. Don't worry so much about that. It's basically saying that if I take a sample, the proportion I get from that sample is the best estimate of the population. Now, notation is always a pain in the butt for us in statistics. If you remember, a lot of times we were using English letters versus Greek letters. Well, now we're actually going to be on just proportion, be using lowercase p to represent the population proportion. And for the sample, it's p with a little hat above it. It's actually called p hat. So just know that p hat is my sample. P is for the population. And again, the P, populate, yeah, you get it. I'll say popple. This is a lowercase p. It stands for proportion. Now, a confidence interval is the real drive of this chapter 7. So it's a range of values used to estimate the true value of the population parameter. Remember, parameter is the data value that is describing, an entire population. So if I wanted to know something about all American adults, that would be a parameter. If I want to know how many adults in America believe in the death penalty, that's a parameter. Again, I can't interview them all. That's not going to happen. I can't get that true number. But I can get an interval, a low and a high number, and I can say, hey, I'm pretty sure that the correct answer is somewhere in there. I think of it like a lasso. So the population parameter, in this case, it's a proportion. Yes, lots of P words. So there's some P. Think of it as a little cow. Then that's not a devil. That's supposed to be a cow that I'm trying to lasso. I don't know it, but I can get close to it with a lasso that has a low and a high end. So if it were true that the little cow here was 30%, stick with that. 30% of Americans believe in the death penalty. Maybe I have a confidence interval that said somewhere between, let's say, 28 and 32% of Americans believe in the death penalty. My lasso would catch the population proportion, which is the parameter. Maybe I did a different study and it was 29% to 33%. Still, I caught it in there. It's not necessarily going to be in the middle, but it's somewhere in that group. Now, we cannot be certain that we catch it every time, though. That's the problem. Maybe I did a study and I got a confidence interval. Let's call it, I don't know, 26% to 29%, maybe. This lasso did not catch the cow. So, which still looks like a devil. We cannot be sure. We can be reasonably confident, though. That's what a confidence level is. Most of the confidence levels are 90%, 95%, or 99%. Now, these are corresponding to alpha values you can see there of 0.1, 0.05, and 0.01. Now, these are not the only confidence levels. We can actually conduct a study and be as confident as we want. But there's a trade-off. Here's the problem. If I want to be more confident that my lasso catches P, if I want to be real confident that it's going to catch P, I have to make that lasso huge. Like maybe it's going from 15% to 45%. So if I came to you and said, hey, I am really confident, 99.9% sure that somewhere between 15% and 45% of Americans believe in the death penalty. Okay, I'm really confident, but I didn't really tell you a lot of information. That's a huge range. So yeah, if you want to be more confident, it seems like, why don't we just be 100% confident? The only way I could be 100% confident that I caught the correct answer is if I said somewhere between 0 and 100%. That's the only way I could be 100% confident that my lasso is going to catch the answer. Obviously, that doesn't help. That's not a lot of information. Now, conversely, if I want to be more precise, meaning squeezing that lasso together, if I really want to make sure I get that right number, and I have something between, I don't know, 29% and 31%, I have to give up confidence. Since my lasso is so tiny, I know that I can't be as confident that my lasso is going to catch that cow. So there's a trade-off. Bigger lasso, meaning a bigger confidence interval, correlates to, higher confidence level, but it's not as precise. Conversely, a lower confidence level corresponds to a tighter lasso. So again, there's a give and a take, a push and a pull with this. So statisticians has found the sweet spots to be around these. Now notice that alpha, that is the alpha that we talked about at the top, that Z of alpha. And actually we're going to be dividing it by 2 and you'll see why in just a little bit. But that alpha is the same alpha. On this next one, this next slide, there's really no work that we're doing here, but all the work has been done. So basically, here's what this is saying. Somebody did a survey of 1,007 adults. 85% of them knew what Twitter was. So there's my sample proportion. Again, the little p hat means the sample proportion was 0.85. So they took the percentage, turned it into a decimal. Now, doing some calculation that we're going to learn how to do in just a little bit, they then got a confidence interval. So their lasso went to 0.828 on one end. Actually, should have made this red. That's what my lasso's been. To 0.872. So that's their confidence interval. And the procedure they used had a 95% confidence level. Again, we'll figure all that stuff out. What you need to understand is that the confidence level is not how accurate they feel like their results were. They're not saying, oh, we feel like we calculated things correctly 95% of the time. They're saying the procedure we use catches that cow 95% of the time. So let's say that the actual P, remember, see there's no hat here, was 0.9. It's entirely possible that my little P cow here is 0.9, that I just missed him. My lasso just simply did not catch him. That can happen. I can't know if I'm right or wrong. That's where the confidence level comes in. So 95% would be 19 out of 20. That means that there's a 1 in 20 chance that the study I conducted is just going to miss. And this is trying to show that there's 19 different intervals here that all catch the answer. Maybe my study is just the 1 out of 20 that isn't going to. It's entirely possible. We can't know. That's the nature of statistics. We don't know for sure. Okay, so this critical value is what's going to separate my most likely to occur from less likely to occur. This one, we're going to do just a couple examples real quick. Now realize that we were doing Z of alpha. Now we're doing Z of alpha over 2. So what I'm going to have to do is take the area that's in the tail and divide it in half. You'll see what I mean in just a second. So on example A, find the critical value corresponding to 99% confidence level. Well, I'm basically saying inside of the curve, let's get rid of this as U, alpha over 2. I'm basically saying inside of the curve, I want 0.99. That means the area in both tails, both of these tail areas together, is going to be the remaining 0.01. But I have to divide it in half for each tail. So I'm taking 0.01 and dividing that by 2, which will give me 0.005. So 0.005 in each tail. Okay, so basically this turns into stuff we have been doing. I want to know what z-score has an area to the left of, well, that's 0.99 and 0.005, so that'd be 0.995. If you go to your z-score sheet and you look for 0.995, that's actually going to be one of the special ones, and that's going to correspond to a z-score of 2.575. So that is the critical z value. And actually, if you look on your green table, there's actually common critical values. And with 0.99, it is 2.575. So that's one of the, hey, we can just look it up. I believe it's in the bottom right of your table. For part B, find the critical value. I accidentally hit Cortana there. Corresponding to 95% confidence. Okay, so 0.95 is in the meat of the curve. That leaves 0.05 in the tails, but this is why it's alpha over 2. I have to divide that by 2 to get each tail. So 0.025 is the area in each tail. So if I want to figure out the z-score, z critical value, it is what z-score goes here to where 0.95 and 0.925, that's going to be 0.975 area is left. That goes with a z-score of 1.96, and we've seen that number a lot of times. So that is the critical value. And again, we're going to be using this critical value idea in our further calculations, but right now we're just trying to figure out how to do the critical value. Now in part C, I worded it a little bit differently. And just to give you a little heads up of what I'm doing on this one, I gave you the alpha of 0.16. Now remember, the alpha is split into both tails. So if alpha is 0.16, each tail is 0.08. Well, if we think about that, all right, if 0.08, 0.08, that's 0.16, that means 0.84 is in the meat. So this sounds weird, but this would be saying an 84% confidence level. We'll go with this number that I'm about to find. That's a very strange number, but again, I can do a confidence level whatever I want. I can be 50% confident, 70% confident. Those don't sound very confident. We usually go, like I said, 95, 99, maybe 90. So I am looking for the z-score that has an area to the left of, that's going to be 0.84 plus 0.08, which is, what's that, 0.92, I believe. Oh, looky there. And if I look for 0.92 on my z-score sheet, that should go with a z-score of 1.41. So that would be my critical value. Okay, so Oops, wrong way there. So this is showing that 95% confidence level one that we did, where the Z critical value is 1.96. And it would mimic itself over here. We're only going to care about the positive ones, though. But again, we're taking the leftover after the confidence level, whatever's left over, splitting it into two tails, figuring out the Z score that goes with that. Okay, I'm going to stop this video and I'll start up the next one to finish up 7.2.